So first of all, I would like to thank Itsuma to have invited me for this talk. It's my first real conference since 2 years, so it's a real pleasure to be with you. And it's also the good times to reconnect with some of our customers. So as you are going to see on this slide, I am part of the material, so I am completely on the right side for you. And my talk today will be about the material digital transformations, a key ingredient to speed up innovation and design process. What I propose you is to start by basic questions. So, is there any industrial product that are not made of material? You are going to find material everywhere. We have material in the mouse, in the laptop, in your phone, in your car, in your bike, etc., etc. So material are really at the heart of all innovations and design. So when a design or an engineer or structural engineer is starting to study a new product, he needs to select or decide in which material he wants to do this product. Is it steel, is it wood, is it plastic, is it composite? This will have an impact on the decision that he's going to do on his design. On the top of that, it will impact also the productions, because you are not going to produce a product made in wood in the same way that you are going to do it with the composite. So you need to integrate that also in the decision of your manufacturing process. And finally, the material will also impact the quality of the part that you are going to produce. For the performance, of course, but also for the challenge that you are going to have during the manufacturing. Do you have to consider warpage? Do you have to consider some fiber waviness in composite, for instance? So a lot of connections, a lot of things to check at the level of the quality that are related directly to the material. So, the goal of our team, the material team, is to provide you solutions and tools to unlock the power of the material. And the first point for us is to work at the level of the material data management. So all of you in your company, you are going to collect material by different ways, from the lab, from a data sheet that you can find on the web. And so you need to organize this, you need to share this internally and make sure that your engineer can find in an easy way these informations. This will be the goal of the material data management. On the top of that, we can add also some Digimat material laboratory. So there, the idea is to provide you tools, simulation tools, to better understand what is the behavior of your material, and to perhaps be able to complement the information that you have collected from the lab on your material. I will speak more about it later. And to come back on the point of Nicolas today, we can enrich this digital material laboratory with some AI ML solutions, do what we call material informatics. So based on the specific strategy of material data enrichment by coupling the AI ML with the digital material laboratory. So of course here we are at the stage of the material. So it's good, you are going to understand the material, you are happy, you know what is the behavior, the stiffness, the strength, whatever. But to move to your product, you have to think about how are you going to manufacture your product, and what could be the dependency between the material, the manufacturing, and the final performance. And this is the goal of the box that you have on the top right corner, that is the multi-state simulations. So there we are going to create this coupling, this bridge between the material, the manufacturing process, and the final part performance. And a good example for that is the polymer additive manufacturing applications. So we are going to be able, in our solutions, to simulate the 3D printing with plastic material, predict you the warpage during the manufacturing process, for instance, but move also to the part performance by taking into account the influence of the position of the part in the printer on the final mechanical performance of the product. So let's go a bit more into the details. At the level of the material data management, we are first going to start by collecting all the information. So first, it's an enterprise solutions. So our goal here is really to provide you with tools that will allow you to organize the material informations for all your company. So you are going to import all your informations inside. You are going to connect these solutions with some also external data bank. And then the designer or the CE engineer will be able to go there, to go in this material center or material data management to identify what is the best material for you. So you'll be able to look at the performance of the material, to compare it, and then to transfer it to his favorite finite element simulation code, for instance, to use it on his product. What is interesting is that we are not going to collect only the information directly of the material, but we are going to collect also information about how this data about the material has been obtained. So it's where we are speaking about manufacturing method. So if you are doing some tensile test on a given specimen, how the specimen has been manufactured, what was the condition for the manufacturing, in order to keep a complete traceability on the source of the data that you have. Without forgetting the fact that we can also support you in evaluating the sustainability and the compliance of the material that you are going to use. So this tool that is called Material Center is there to offer to your company a unified data source with a global access to all your users, internal users, with highly secure protocol in order to give access to some information to only some engineer, with a full traceability. And we can embed in this tool some solutions based on AI/ML solver, let's say, to enrich the material information. Let's now move to the unlocking of new material data. So inside our second solution that is called DigiMat, we are going to offer different solutions to allow you to study the performance of your material. So first of all, we are going to speak about various types of materials. So we have the classical unidirectional composite, but we can do also in foams, in SMC and SFRP, in different types of metals. So it's a multi-material solution that we have here that will be able to cover multi-physics, so mechanical, thermomechanical, electrical, thermal, but also electromagnetic, and multiple performance. So we can speak about quasi-static testing, stiffness strengths, but we can go also on creep, on some fatigue stuff. So a very large portfolio of performance that can be covered by these different solutions. And we are not going to have one unique tools to predict you the behavior of the material. We are going to work between finite element solutions, mean field homogenization solutions, in order to offer you the right tools for the predictions that you would like to do or the study that you would like to do to better understand your material and be able to take the right decisions on your material design. An example here of coupling these solutions that I just explained you before with an AI/ML solver, where you can imagine that you have on the left all the material that you are going to use in your company. And for all this type of this material, you need to have some properties. And of course, you would be very lucky if you had all the properties that you need for all the material. There is always some properties that are missing. And so the question is how to fill the gap. And this is the goal of our previous solutions, enriched by AI/ML engine, in order to fill the gap in this matrix. So all the blue square that you have there on the right are going to be virtually computed, either by just an AI/ML solutions or by an AI/ML solutions plus some physics-based meta model, or AI/ML plus virtual testing based, for instance, on finite elements simulations. Now that we have explained what we can do at the level of the material, it's time to move to the level of the manufacturing. And there, for us, what is very important to understand at the level of the manufacturing is what will be the consequence of the manufacturing on the microstructure of the material. If you think to a unidirectional composite, if you think to short fibers, reinforced plastic, the manufacturing is going to directly impact the orientation of the fibers, could create also some defect, and so you need to capture that to be able to predict correctly the behavior of your material in your product. And so this prediction of the microstructure, or how to know the microstructure, we can know it by simulations, run a few simulations with various types of products that reproduce the manufacturing process. Or you can measure it directly on the machine. If we think about a 3D printer, is measuring the tool path will give us already a good information on how the material will be inside your product. Or we can do also by CT scan. And there, being part of Hexagon Manufacturing Intelligence, give us the opportunity to have connections with volume graphics that will allow us to post-process the CT scan, take information from the CT scan inside the simulations. With the objective to reduce waste, because by better understanding which type of defect could be generated by your manufacturing process, you are going to study more your manufacturing process proactively, and so you are going to have to do less trial and error to produce your final part. Also, very important, you are going to save time to market, of course, because less trial and error, so less work to do, and you are going to enhance the quality. I was speaking about volume graphics. Here, just one slide. where we explain what we can do with volume graphics. So you are going to do your CT-scan, you go in volume graphics. In volume graphics, you can study various types of things. It can be the orientation of the fibers, it can be the waviness, it can be the porosity, many different things like volume fraction of fibers also. So all type of real information that we can import inside your simulations to have a virtual model that is much closer from the real part as it is produced. And it's the example that we have here with a casting process where you can see all the porosity. These blue and red dots are porosity inside the part. And so we can take this information from the real part, integrate it inside Digimap to predict with Nastran, Mark, or any other FEA software available on the market, the final stiffness and strength of the part as it is produced, taking into account the defects. We have many other applications for this type of thing. So we can speak about crystallinity and curing, so we can study your curing process by using some multi-scale material model and tell you which degree of cure you are going to obtain after a given cycle of temperature. We can do some study of effect of defect by looking at the effect of the waviness, by looking at the effect of gaps between the toe, by looking at porosity. We can move progressively to failure and damage by looking at decohesions between fibers and resin, by delaminations between the ply of a stacking, looking at some progressive failure, how the failure is going to propagate inside your composite. Without forgetting, of course, an important component, that is the variability. You can never be sure that two materials that you are going to get have exactly the same properties. There is always a bit of variability on the material constituent, on the orientation of the fibers, on the amount of the fibers. So take into account the variability and see the impact, be able to evaluate the impact on the stiffness and the strength is definitely important. Now that we have understand what we can do at the level of the material and take into account the effect of the manufacturing of this material, it's time to move to the level of the product itself. And it's here that we are going to create this bridge, as I was explaining before, between the material, the process, and the part performance. The goal to create this bridge is to be able to really optimize the design of your part by using at the best possible the properties of the material. So the goal here is, for instance, to lightweight the design and to reduce also, by better understanding the influence of the manufacturing process on the final part performance, to reduce also the design time. This is very important. Reduce the material waste, reduce the development cost. A few years ago, one of our customers, Vibra Acoustic, has demonstrated that they have been able to reduce by 40% the development time of their engine mount by using this type of technology, by integrating the effect of the manufacturing process much earlier in the design loop of their engine mount. So here you have a few other examples, beside the one that I just mentioned. You have a first one here with Faurecia and Solvay, where Faurecia has redesigned the seat pan moving from steel to plastic, leading to a reduction by 50% of the weight. You have a nice applications, the second one of NVH, where we are going to take into account the complex behavior of reinforced plastic material. A plastic material does not show the same behavior in vibrations than a steel material, and so you need to use some specific material model to capture the damping of the plastic in this case, and how the damping is influenced by the reinforcement. Here we have a nice work that has been produced with DSM. Lucien Devon is in the room. He could speak about it even more than me or better than me, where we are predicting the lifetime of their reinforced plastic material to be able to move at the part level and tell you, as function of the local fiber orientations, what will be the lifetime of your product. And finally, at the level of the additive manufacturing, we have a lot of collaboration with different printer manufacturers and different material suppliers. And here you can see an applications where we have predicted the stiffness and the strength of a component that is made of reinforced plastic material for 3D printing. So, just to almost at the end of my talk, and just to give you a first view on what to come next. So we are going to still have two releases this year. So one release will be for Material Center, the 2022.3 that will be planned for November, where we are going to improve the workflow to request informations and approval requests for the material. We have worked also on the post-processing of the data, so how to offer better way to analyze the data that you have inside your database to select the right material for you. And also for the continuous fibers composite, we have integrated a new statistic tools that is available in CMH for basis calculation, so to be able to know the allowable of your material. In Digimat, it was difficult to do a choice because we have 17 new developments for the next release that will be planned for December, so it's quite a lot. So I took just few of them because it was impossible to list all of them and give you a short explanation on all of them. But first of all, you have to know that fatigue is still a very important topic for us, so we are going to continue to work on fatigue and to improve our integration with CA fatigue and encode. The curing also. Curing is something that for which we have more and more requests from various types of customers, not only in the aerospace field, and so we want to continue to improve our model there to better predict the warpage of the part, to better predict the curing degree that you can get after your manufacturing. At the level of the digital material laboratory, it's important for us to continue to improve the usability of the tool, so in order that you, customer, are going to have a better user experience. So it's why we continue to work on the reverse engineering process that we have to calibrate our material card, especially in failure and strength. And for the customers using Digimat VA, so the solutions that is used to predict the allowable in case of continuous fibers composite, we have integrated a real-time monitoring. So this means that you don't have to wait the end of the simulation, so several minutes to be able to know what will be the stiffness and what will be the strength of your material. You can see it along the computations, which is quite interesting, I think. And without forgetting additive manufacturing, that will allow you, where we are going to develop more capabilities to simplify your life, to compare your simulation result with the real parts. So you can use some tools from Hexagon to scan your components, to post-process the scanning and integrate the result of the scanning inside our simulation tools to compare the simulation result with the real parts. And we are going to support also a universal format for 3D printing that is called 3MF, and that is based on a big consortium. So this will become one of the standards for the future. Time to arrive to the conclusions. So what we want to say here in the conclusions is that, of course, the digitalizations digital transformations will not happen immediately. It's something where we can help you. We have a lot of tools inside our portfolio at the level of the materials, but also in Hexagon in general to support your digitalizations. And you have to know that all solutions are agnostic. So this means that many things that I have shown you today will work with Hexagon solutions, but will work also with solutions coming from our competitors. I could mention many finite element code that we are supporting that are not part of Hexagon at this moment. And what I would like still to share with you is that Hexagon, as it has been illustrated in the talk of Virginie, is developing their own product. So they are developing scanner, they are developing different type of real physical product. So they know what means digitalizations, they understand the challenge that you are going to face during digitalizations, and we are at the correct place to support you and to help you in this way. Thanks a lot.